This conference will now be recorded.
So welcome to the 50th, meeting for OCP TAP. So we had like a bunch of cancellations and so on. So last minute things, and we have a talk today by Christopher Volt, right? So
Christian Voigt, yes.
yeah. So I think I didn't get the bio, so we'll basically hand it to you, and I make you also the presenter, so you can start with the slides, and we'll take it from there. Please introduce yourself, and we'll take it from there.
Sure. Thank you, Ahmad. Yeah, to start maybe with a little bit of background about me. So I'm Christian Voigt. I'm a field application engineer of ProTempus and formerly Trimble. As you may know, we changed our name and we are now independent since May, the time and frequency group of Trimble. So I'm with that group for more than 7 years now. And with Trimble in general, I think for more than almost 17 years. I have been active with GNSS and GPS before that time even. So yeah, it's quite a bit of time since I'm active in this arena. And yeah, today I want to present you, let's see, where's the, do you already see my screen?
Yes, we do.
Yes,
okay,
we can see.
Yeah, okay, great. Then let me enlarge this. I hope you see the presentation mode without the overlay windows from the meeting, right?
It's not. Try again. Press that one. Is it? Do you see the present? If not,
right.
You have to switch the screens, I think.
This not pausing. Does that mean? Okay, so now you see my presentation, right?
Yes.
Okay, great. Yeah. So I think, well, it was kind of a short notice invitation. I believe, as far as if I understood demand correctly, I have like 30 minutes, like 20 minutes plus something for some questions, maybe. Is that right?
Feel free. Feel free. You can go through like 45 minutes to 50 minutes,
Yeah.
no problem.
Okay. Yeah. Well, today I want to show you basically a very condensed version of a training that usually takes like half a day. So I try to condense everything very much, and I also may browse through some of that very quickly. The presentation today is about timing basics, and the underlying technology that we are using in our receivers to reference to the official international time reference. If we can tell that there is one, because let me explain that to you later, what we are actually referencing to. And first of all, let's start with some short timing basics. So time and space actually are linked to each other by relativity. So if we come to very small time units like the nanosecond, which is a billionth of a second, we are in the relativistic time arena. Actually, the velocity of the space vehicles, of the satellites, make a difference for the computation. So this has to be considered in the computation of the time outputs of our products. Time bases actually until the 1970s were based on astronomical observations based on the Earth rotation and the revolution of the Earth around the Sun. So at that time, there was the Greenwich Mean Time, or in the military also often referred to Zulu time, which is what we know as the time of the 24 time zones, with the origin at the Greenwich, England location. But that was not enough and not stable enough because the Earth rotation is not constant. Modern technology was not able to work with this unstable time base. So that was replaced by UT, by Universal Time, and by UTC, Universal Time Coordinated, in actually 1972. So it is not that long ago. And the basis for those modern timekeeping systems is the TAI, or Temps Atomique International, which is French for International Atomic Time. And that is high precision time standard. And that is the basis for, sorry, make this a little bit smaller so that I can read it here. So that is the basis for the timekeeping of most of the world today. And this is actually not a single reference clock. The TAI is the weighted average of the time kept by many hundreds, over 400 atomic clocks in currently, I think it's more than 80 national laboratories worldwide. And the average and the steering of all those clocks is calculated and coordinated by the BIPM in France. And they have a list, so you can look up which national labs are participating in this clock ensemble. And the way it works is that all these hundreds of atomic clocks are compared using several different technologies, for example, and among them GPS signals, as well as two-way satellite time and frequency transfer technologies. I explain that on the next slide. And those the oscillators of those atomic clocks are averaged, and very small adjustments are made so that all those clocks should never deviate from the mean average by more than 2 nanoseconds per day. And the SI second, the international reference unit for the second, is defined by the oscillation of the cesium-133 atom in the cesium clock set, many of us know. I mentioned time transfer, so there are different ways of doing that. So, for example, there's a technology called common view time transfer. That is when two observers, for example, the clocks UTC-K1 and UTC-K2 in two different countries, for example, are looking at the same satellite. So they see the same signal coming from that satellite, and they can then compute based on the travel time of that signal when this time signal was originated from that satellite. And 1972, obviously GPS was the only satellite system that supported that. So GPS is the underlying time transfer function for this common view time transfer. Other technologies are used in parallel, and they, for example, using two-way time transfer methods. That is pretty much similar to what we are using in PTP today. So one clock provider, the UTC-K1 clock, sends a signal to a telecommunication satellite, and that is being echoed by the UTC-K2 station and sent back the same way back to the UTC-K1 clock. And then the total transfer, the total travel time can be measured, and the two stations can exchange the measurements, and then they can compute the adjustments they need to make on their local clocks. The UTC that is now more or less considered the global standard time is based on this TAI, but TAI is a continuous time. It does not have any leap seconds. It does not have any discontinuity. You can consider it just a counter that runs forever without any interruption or any discontinuity. But UTC has to be adjusted because TAI is an atomic time, and this atomic time is not actually synchronous with the uneven movements of planets and stars. So the astronomical time does not follow our precise atomic clock definition. So we need to adjust the UTC from time to time to the actual rotation of the Earth. And that is done using an integer number of leap seconds. Leap seconds in this context is the difference between UTC time and TAI time. There are other types of leap seconds, for example, the GPS to UTC leap second, which I explain later. But that is basically how we adjust the atomic time to the astronomical time, which is needed for astronomical purposes and our calendar system that we are using. The UTC is what we all know as our 24-hour timekeeping system, including the calendar concept that we are using. But national clocks, national reference clocks, are steered with tight limits to other nations' reference clocks, and the legal time in certain countries is referenced to their local standardization institute, which is, for example, in the USA, the NIST, as well as the US Naval Observatory. The US Naval Observatory is actually the reference clock for the GPS time base. Russia uses the UTC SU. SU is Soviet Union, which is no longer existing, but it's basically the old system that they used in Moscow for their national reference, and that is the clock that steers the GLONASS satellites. The BeiDou system is controlled by the Beijing Radio of radio measurements, and it uses the China national UTC BIRM clock. Now, GPS time is the system time of the GPS system, and I'm just limiting my explanations here to GPS because the concept of all the global GNSS satellite systems is pretty much the same. So if you understand GPS, you also understand all the other GNSS systems, more or less, with some differences, but the underlying principles are pretty similar. So each of these systems has its own system time, and in GPS, it is what we call GPS time, which is a continuous time, and this is divided into a time of week counter that resets every Sunday at midnight, as well as the week counter, which increments each Sunday midnight. So each Sunday midnight, a new GPS week starts, and then the time of week counter is counting into that week. But the original GPS week counter only had 10 bits, which is 1024 counts. So after that, that timer rolled back, and that is called GPS week number rollover event. And that happens every 19.7 years. The last one was in the year 2019, and the next one comes in the year 2038. Now, other GNSS systems use different counter size, so they can survive much longer with that counter on a continuous basis. For example, Galileo supports, I think, up to 127 years with its counter, and there are now more modern technologies to keep the calendar continuous, but we still have to deal with this in the more simpler GNSS receivers. But it is up to the receiver to convert the GPS week and time of week information to the normal date and time. I mentioned leap seconds. Now we have another type of leap seconds because GPS time is a continuous time, and it differs from the UTC time by an integer number of leap seconds. currently that leap second number is 18. Other GNSS systems have their own leap second offset, which is different from the GPS leap second offset. So we don't have just one offset for all the systems. We have multiple offsets, and they are not the same. So that leap second method, the TAI to UTC and the GPS leap second thing has been a pain for many programmers and for many technologies. And there is a continuously ongoing discussion if that is being replaced or if it's being improved or what happens in the future. But the organization that is in charge of defining the leap seconds, the ITU-TR, has postponed their next discussion until the next World Radio Conference in 2023. So there will be no change, at least until then. So yeah, why do we need synchronization? I'm not repeating all the things that we have seen on many presentations before. You all know why we need that, for which applications, but what we actually need to do to achieve synchronization are two steps. We need to have identical oscillator base frequency in two or multiple clocks, and we need to align their phase. So why do we do that? So the first step is synchronization. We have two oscillators, for example, the rubidiums or CSECs or whatever you have on your tab card, and they are providing the base frequency for the PPS outputs and for the reported values in the PTP packets. So we need to align those two oscillators to the same base frequency, and that does not necessarily mean that they are already phase aligned, because they can have the same base frequency. That means they can run on the same speed, but not necessarily transition to the next second at exactly the same point in time. So what we need to do, we need to align their phases by the phase angle theta. Now there are different ways for synchronizing two stations A and B, and for example, we could use two high precision clocks at both stations A and B, which is very costly at the atomic clock level, and it still requires a frequent time transfer to adjust both clocks, because they have only stability for a certain time period. So other technologies are using permanent or temporary links between two stations A and B that could be wired or wireless, for example, using the old E1T1 telecom systems, XDSL, Ethernet like SYNC or wireless LAN, or PTP, which is of course one wired or even wireless way. Wireless not good, but thinkable. Or we could use direct radio links between stations A and B. And one of the radio links could be actually GNSS. So talking about clock accuracy, here's a nice diagram. You can look at that later if you want to have some history fun. Because since the last 2000 years, the clock accuracy has improved from hydromechanical clocks to optical ion traps, and that has led to a multi-magnitude improvement in the clock stability, far below a picosecond in the best clocks that we have today. So this is actually a very old image, but it gives you an impression of how the US Naval Observatory clock ensemble looks like. It's basically a wall of racks with a lot of atomic clocks, and in the front you see, I think, hydrogen masers, and they have other types of clocks meanwhile. So they have multiple clocks running in their lab, and they are all being averaged and adjusted against each other. but the single one and the only official true time reference is actually the main physical PPS connector, may it be BNC or N-type or whatever, in the standard institute, such as NIST in the USA. So anytime, anywhere else than there on that single connector requires a time transfer from that single point of truth. The time transfer to some remote place, such as a grandmaster clock, a PTV grandmaster clock in your data center, that may be traceable, but it is subject to errors. And even if we use GPS or GNSS in general, there is an error budget and even test equipment that you may use for validating the clock accuracy of your, or maybe of our products in on your tap card, is subject to that error budget of the time transfer, and that must be considered because the test equipment usually is in the same synchronization level because it is also using GPS or GNSS as the underlying technology as the device under test. So you cannot claim that you have UTC synchronicity without frequent and traceable adjustments to the official big UTC clock ensemble. Now, what does that mean? So you have, it's not really a cloud like the internet, but the clock ensemble is actually some sort of a specialized cloud that contains all these hundreds of primary atomic clocks. And I just listed a few of them here as example. But the special one here is the USNO clock. That is basically the time base for the ground station clock of the GPS system or the other GNSS systems in other countries with their national institutes. So the traceability goes all the way from that clock ensemble towards the other end that is connected to the actual GNSS receiver, for example, inside of the PTP server. So the PTP clients get their time from that PTP server. The server gets that time from the GPS satellite. The GPS satellite is controlled by the ground station clock, and the ground station clock is the one that is linked to the clock ensemble that is providing the official UTC time. Now, as I explained, different countries have their own legal time institute and primary clock. So they are not 100% aligned with each other. For example, this is just an example diagram here that compares the UTC, US Naval Observatory clock, to another official clock, which is the UTC Soviet Union clock in Moscow. And those clocks are then using time transfer to the clock of the GPS system, the GPS-T, as well as to the GLONASS system clock, the GLONASS-T. And all of that, all of those time bases have a time delay towards each other because they are steered towards each other, but they are not zero. So we have to consider time differences between even the reference clocks we are referring to as the official UTC time.
One question, like, do you mind questions to be asked during your presentation, or you want them in the end?
I think let's move that to the end because some of that may be answered during the presentation already. So maybe if you could move it to the end, that I think would be.
No problem.
Thanks. Now, this diagram actually just compares two different GNSS systems, but actually worldwide we have a multitude of GNSS systems. This is even not the latest plot because I just saw that Korea has launched its own support system satellite for GPS. It's I think it's called KSAS, and this is under constant evolution and yeah, also in system improvement because, for example, GPS is also modernizing their satellites. So all this is a dynamic system. It's not something that is constant. I'd like to spend a few words about the oscillator types, and I believe most of you are very familiar with that. I go very quickly through that. So just to understand the differences here, the rubidium oscillators are pretty expensive, but they are more stable than quartz crystal oscillators. However, rubidium oscillators have their disadvantage. They don't have that longevity of quartz crystals. They have issues at high temperature. So the application and also the cost range of those clocks is limited by the application. Quartz oscillators, on the other hand, have aging effects and they have drift effects. Aging is something that is internal to the crystal because it's aging over time. But drift is something that is induced by external influences such as the temperature, environmental temperature, vibration, and other factors. But we can use GNSS to discipline oscillators, which is what the TAP card does, because you have two GNSS receivers on the TAP card that are disciplining that oscillator. And this is a diagram of what is actually happening there. So the disciplining happens based on the reference time pulse provided by the GPS or GNSS receiver to synchronize to the UTC reference, traceable as per the path that I explained earlier. And the overnight oscillator is then controlled, and this loop filter here is actually what's going on in the FPGA of the TAP card. So here's an example of with an OCXO that could be a rubidium or a CSAC clock or any other stable oscillator, but that is the principle of a GPS or GNSS disciplined oscillator. Oscillator disciplining is like you turn this with a feather. You turn something very, very heavy with something that is very, very light, and don't put much force on that clock because you really adjust this with very, very tiny steps. But over time, it becomes very stable and very accurate. Now, we have seen that GPS depends on timing, but timing also depends on GPS. So what we need to understand is that the atomic clocks in the GPS satellites are free running, and the control station compares the satellite clock frequencies with a master clock on Earth, which is UTC synchronized. Then clock correction factors are sent to the satellites, and the carrier frequencies and all subsequent frequencies are synthesized by the satellite based on its internal own atomic clock, actually multiple clocks per satellite, and those clock correction factors. This is the diagram of how the GPS system and all other GNSS satellite systems are conceptualized. We have three segments here. We have the space segment and the control segment and the user segment. Now, what are these? The space segment is actually the ensemble of satellites of one constellation, and they have multiple atomic clocks per space vehicle. Now, the signal of their radio frequencies is very, very low on the Earth's surface. So it is minus 120 dB milliwatt to minus 130 dB milliwatt in open space conditions, which means not inside, which means basically outdoor with unobstructed sky view. And it is a very, very weak signal. What you can actually see here in this diagram, which I took from a study, scientific paper, that the new Block 3 GPS satellites have a total transmit power of 300 watt, and the biggest contributor of that power budget is actually the new L5 frequency, which is much stronger than the older L1 and L2 frequencies. So the signal power is being improved in modern satellite generations, but it is still very, very weak and below the RF noise floor due to thermal effects on the Earth's surface. The GPS control segment is closed loop. That means there are monitoring stations around the equator, which are shown here on that map. And those stations monitor the time and the ranging signals permanently, and they report it back to the ground station in Colorado Springs. And they and the ground control station sends these corrections to the satellites. So it's a closed loop system. And the user segment, those are actually the GPS or GNSS receivers. And I just show some of them, ours, to show them here on that image. The satellites are in pretty high orbits, medium geostationary Earth orbits in 20,200 kilometers altitude from the Earth's surface in 6 orbital planes. And they are positioned so that 5 satellites are visible at all times anywhere on the planet at minimum. The next slides are going more into explanation of how we are actually getting the time from the satellites. And we are using radio signals. So the GPS signal has actually 3 components, actually more than 3, but the old traditional system had 3 components. One is, and the most basic one is the course acquisition code, or CA code. Then we have the nav data. And we have precise code, which is Y code when encrypted for the military. And the new L5 signals, they have a new code scheme that is the NH code that is only available from Block 3 satellites, or in other implementations also on Galileo satellites, for example, under different names. So the CA code is basically the tracking code that the receiver needs to acquire and to track the satellite signal, because they are all transmitting on the same frequency. In case of all GNSS systems except GLONASS, GLONASS uses different frequencies, but all the others are transmitting on a single frequency with the technology explained here. It is a spread spectrum signal, and the code, the carrier signal, is modulated with pseudo-random PRN numbers. They are also called Gold code, after Dr. Robert Gold, who invented that, or ranging code. And currently 33 PRNs are defined for GPS satellites. Other PRNs are defined for support systems, just as SBAS or the EMSA systems. And there are other PRNs for other GNSS systems. In the GPS system, the traditional L1 code has a chip rate of 1023 chips, and that repeats every millisecond. So it is like a continuously repeating code scheme at a chip rate of 1.23 megahertz, which is a distance at the speed of light of approximately 290 meters. So every 290 meters, that same signal pattern in the radio signals repeats. This is actually much improved in the L5 code scheme, which is 10 times as long, and it also repeats every millisecond, but at a 10 times higher chip rate. So that shortens the chip length to approximately 29 meters, and that makes a big difference when it comes to resolving the ambiguity of the code phase, because we now can detect anything that has an extended travel path longer than 29 meters compared to what we could detect with only the L1 signal, because that is limited to resolving the ambiguity in approximately 300 meters distance. That code is quite complex and resembles random noise, but although it's random, it has been selected to be correlation friendly. And we know the code structure for each satellite. So as the code structure is known, it can be locally generated by the GPS receiver. And we can compare the generated code to the code that we receive from the satellites in the radio signals. And when they match, this allows us to amplify and measure the time differential and track that satellite. And when we did that, from the time differential, we can calculate our distance from the satellite, and that is called the pseudo range. Pseudo because we don't know it with certainty, because it comes with errors. So we need to resolve the errors as much as possible and assume that we have a certain range to that satellite. And the computation is based on the equation time multiplied by the speed of light gives us the distance to that satellite. Now, correlation is the method to reveal those signals in the overlaying noise floor, but we have to do that multiple times, hundreds and thousands times of comparing the known pattern against the unknown pseudo-random noise signal that we are getting from the antenna. And when those signals match, then we get a power peak in the correlator. This is an illustration. If the two patterns in the radio signals by chance match, then that correlator would indicate a power peak. That means we detected a real GPS signal. Now, to search for that signal, we have to search over the entire 1024 chips of the CA code, and only a perfect alignment yields maximum power. So we must correlate, we must be able to see that pattern within plus or minus 1 chips to yield any measurable power at all. And that is a challenge because we need to search over a frequency range, because as you see in that diagram, the satellites are moving at high speed. So we have Doppler effects, and the Doppler effect leads to frequency shifts from an approaching to a satellite that goes away from us. We need to search over a frequency range of 7.5 kilohertz, actually. So that gives us a search range, and as the chip length of the L5 signal is 10 times bigger than the L1 signal, this acquisition at the L5 signal is considerably much more difficult than acquiring a signal on the L1 frequency, which is why we need the L1 to acquire satellites before we can actually use the L5 signals, because we don't have that much processing power to do the correlation at the L5 frequency without having the support from L1. It is all a question of processing capacity, but it is substantially more processing capacity that is required to acquire L5. Now, when we have that acquisition from the CA code, then that gives us the range or distance to the satellite, but it is containing errors in the measurement. Some of these can be corrected, some can only be maybe detected but not be compensated for, and some are maybe not detectable or not possible to compensate. But the basis of the detection and possible correction is the data that we get in the NAV data from the satellite. NAV data is a signal that is transmitted in 30-second frames at pretty low bit rate. We can see here how it breaks down, how long it takes to actually transmit the relatively small amount of data. And there are multiple components in the NAV data signal. For example, there are accuracy and health information about each satellite, which is actually a predicted accuracy because we can't measure it 100% accurately. There is a self-indication of satellite health, and then there are system information like the almanac and ephemeris. The almanac is rather coarse, but provides data, for example, the leap second offset between GPS and UTC, which we need to compute the local time. The ephemeris is what provides us with the precise orbit data that we need to know for the position computation. Now the ephemeris is used to compute the precise distance, and we do this in 4 pretty easy steps actually. So one satellite gives us the distance to a satellite on a sphere, of the surface of the sphere around that point in space. 2 satellites will give us the position somewhere on the intersection of 2 spheres, which is basically a circle. And a 3rd measurement narrows that position to 2 points on that circle. And with a 4th satellite, we can discard a nonsense point, which could be out in space or moving at very high speed. And in addition, we get redundant pseudo-range measurements, and they can be averaged, and that allows the receiver to cancel the internal local clock error of the receiver. And that is the basis for the PPS computation. So there are some jumps, actually not just position jumps, but also timing jumps. And the biggest contributor to those errors are multipath reflections. And they occur when the signal bounces off from objects before getting to the antenna. And that actually extends the travel path. So this is nothing else than reflection that extends the travel time, and that causes the multipath error. That can cause time jumps and fluctuations. And this is especially problematic inside of buildings because then basically the receiver works only with reflected signals, or to the majority with reflected signals, and only a small portion, if any, are direct on a direct line of sight to the satellite. And that is even true for re-radiated signals from a rooftop antenna. Jamming is an effect that basically saturates the front end, so that can have a lot of negative effect on the tracking. It can even block the reception, and there can be multiple sources. There can be internal jamming from the system. You can have parts of your system, such as displays, power supplies, and so on, that interfere with frequencies inside of the GPS receiver. This is a very sensitive system because we work below the noise floor. We need to be very sensitive in order to have something to use for the time computation. So we must take care, or the system designer must take a lot of care to avoid any noise in the system. But that could actually also be too much antenna gain, because we have this nice sweet range of gain for our front end. But if the antenna blasts too much signal power into our front end, then that can cause jamming, which could cause bit errors in the nav data decoding, or which could cause false correlation, so that we could see ghost satellites or the same satellite twice in the space. So that is also some point that has to be considered. And then there are other external jamming sources that can come from outside of the system. And possible sources are TV transmitters, radios, radars, anything that interferes with the in-band frequencies of the GNSS signals, or even harmonics or subharmonics out of the original GNSS frequencies. For external jamming, there are methods to keep them out of the system, for example, with bandpass filters in the antenna, or with special antenna with special antennas designs, such as resistive ground plane or choke ring, or very advanced CRPA antennas. but they are pretty costly. So that is a very specialized anti-jamming technology, but it can be very effective actually. The biggest natural contributor to the error budget are ionospheric effects. And the ionosphere is a layer of the atmosphere filled with charged particles that are generated by sun radiation, which is ionizing oxygen and other atoms in that very high atmospheric layer. And that layer reflects the signals, which is similar to multipath, but it's a natural source, and it can considerably extend the travel path of GNSS signals, especially at low elevation satellites. So this is the biggest contributor of the error budget, can cause up to 5 meters of position error, or more than 15 nanos. I think it's like 20 nanoseconds of pseudo range measurement error in a GNSS receiver. There are other types of errors, satellite errors, other atmospheric errors, or noise. So the total position error budget is around 10.3 meter, which is around 33 nanoseconds. Some of that can be compensated, some cannot. And that is where dual band receivers have strong advantages, because in traditional single frequency receivers, we can only model the ionosphere based on models that we get from the nav data message or from other external correction data sources. But in a dual frequency receiver, we receive two different frequencies on the L1 and L5 band, for example, and they are affected in different ways by the ionospheric reflections. Now we can real-time measure the influence of the ionospheric effect, and we can subtract that from the error budget. So we can completely remove that error by using the two different frequencies. On top of that, the higher signal strength gives us also a much easier time to do data-less signal acquisition in obstructed and in unfavorable conditions. Also, that L5 band is approved by the ITU-T for safety critical applications such as aeronautical navigation services. So it is protected internationally against other technologies running on that frequency range. So that band allows us to do advanced anti-jamming and anti-spoofing technologies on dual frequency receivers that we cannot do on single band frequency receivers. Here's an overview that I found in a paper that details on it. It's relatively small and a lot of text, so I just provide that here for interest on reading later. Now, mitigating the multipath and spoofing is essential for the data integrity and reliability, and we do that with a technology called TRAIN. So we perform integrity checks on each of the pseudo range measurements, and this integrity checking allows us to detect signal anomalies and isolate those signals from the timing solution. So our technology allows us to provide 25 validity indicators with detailed status information of the current signal condition. And we can do that per satellite, per constellation, and per the overall combined solution. So this provides you with a lot of information of the local signal quality in your application environment. Now, what makes a position, velocity, and time receiver different from a dedicated timing receiver? The single satellite allows us to know the time with only like 100 millisecond accuracy. But for precise synchronization, we must know the pseudo ranges in order to calculate the signal travel time precisely. So we need a precise reference position or a 1 second position update. And that indicates that timing receivers are stationary, whereas navigation receivers are moving. Timing receivers have therefore special features. They have a self-survey where they average 2,000 positions to come to that reference position. And they have position integrity monitoring to detect if that antenna's position has moved. And they have eventually technologies like holdover, which is basically what you do on the tap card by having that disciplined oscillator to provide holdover when GNSS signals are not available. Terrain improves the output, especially with respect to the reliability and integrity. So it's not an accuracy feature, it's an integrity and reliability feature. And I think one of my last slides is about the sensitivity, which has been a big topic in the past. But actually there are some theoretical limits of how far you can drive sensitivity. And that is basically the information theory, because minus 142 dB milliwatt is the barrier where bit edges in the nav data message are undecipherable. That means we can no longer decode the ephemeris. And that means we can't do a cold start, we can't acquire new satellites below 142 dB milliwatt. So if a satellite that is being tracked drops out of sight, we cannot track a new one anymore because we can't decode its ephemeris. So that limits the acquisition sensitivity based on theory. We can't even drive that further with amplifiers. And that is a point that we need to consider when we look at a GNSS receiver system. The system is not just the receiver itself. The system consists of the actual receiver module plus the GNSS antenna, and the antenna has substantial influence on the system performance. And there are other factors like cables and connectors, as well as active components such as amplifiers, filters, splitters, re-radiators, peripheral circuitry, and as well your environment. Because if you are in an urban canyon or indoors with a lot of reflections and objects, that affects your signal quality at the antenna. And I've seen that in another presentation in this OCP forum, where PCTEL emphasized the need for a good antenna for good receiver performance. Now, all of that should be looked at when the system performance of a GNSS receiver or a primary reference clock for PTP, for example, is being assessed. And I want to conclude with that, and hopefully maybe we have some minutes left for questions, if anything has not been answered yet. So I extended my time, but hopefully I think I hope you found it interesting and you got something from my presentation today.
Thank you, Christian.
Thank you.
Okay, Lasse, do you have a question?
Yes, I do. Sorry, I'm trying not to burn myself in the kitchen here. Okay, yeah. So firstly, I thought this was very interesting, and it was particularly rich in technical detail. Okay, this was technically very, very good.
Thank you.
My name is Lasse, and I make something called the PTP squared, which is a particular thing which in many ways philosophically looks at timekeeping in a different way. And what I want to ask is this, okay? So with UTC, you detailed excellently how you have at places like NIST the clock ensemble, right? Where UTC is derived from a whole bunch of clocks using statistical methods. And then you described how from there you have GNSS systems that disseminate time. So not only do you have in the GPS constellation different satellites, each of which you can get time from, but you also have different GNSS constellations, and if you have a Grandmaster clock somewhere in the data center, you might set it to obtain time from GPS, GLONASS, Galileo, Baidu, and so you look at all of them at the same time. But from there, the philosophy really changes, right? From there, when you disseminate PTP, you then rely on Bestmaster clock, which says, let me get the time only from a single source, all the way through the hierarchy to the end consumer of time, instead of, as is the case in the upper layers, getting time from lots of things at the same time. Why do you think that the philosophy changes from the ensemble method in the upper layers to the single source in the lower layers? That's my question. Thank you.
Yeah. Yeah, that's a very good question, and that is actually also a pretty challenging question, you know, because officially and legally, a country like, for example, US, they refer, for example, for a financial transaction, they would transfer to their NIST clock as the official time reference. Now, for example, the clock in Moscow or the clock in Beijing might differ, might have an offset of a few nanoseconds between their system clock and the GPS system clock. So the timestamp of that financial transaction may be different if you have a PTP master clock that is running in China from Beidou satellites, or in Russia from GLONASS satellites, even though all the timestamps are basically referring to the so-called Unix time format, which assumes that there is a single true time, but in fact it is not, and it is on a nanosecond level, which we are having today in our current products, becoming relevant, because in the past, when we talk about milliseconds, microseconds, you won't see that in GNSS receivers. You can't decipher the system time differences. Maybe you can decipher it between, for example, GPS and GLONASS, because we know that GLONASS had some fluctuations in the past, which could go up into microsecond level actually. So it can become relevant, and it can become important what time base you are setting in your PRTC unit that runs your PTP server, for example. So it is a question of configuration, and it is also a question of the underlying receiver technology. Because there is a weighting of different constellation system times against each other. And for example, in case of our receivers, because we need to combine all these different system times, what we do is we all refer it back to GPS time internally, and from there we compute what we call the UTC alignment of the PPS. But internally, we compute, for example, the Beidou time that we get from those satellites based on measured offsets. We compute that back to GPS time. And we always recommend to include GPS in the set of received satellites, because only then you can measure the real currently active offset between GPS satellite time and other constellations. You may rely on values that, for example, Galileo satellites tell you, but you will only know if that is true if you measure both satellites in parallel. So we always recommend to include GPS in any time synchronization constellation, because then we can measure it and we know it for sure. I'm not sure if that answers your question.
So one thing I'm wondering, it's like, if we have more processing power, which I'm assuming, again, with improvement in technology and so on, we have like, say, more powerful microcontrollers and so on. Can we expect better performance from GNSS receiver?
Well, actually, we are pretty much at the theoretical accuracy limits that we can achieve with that. Because as I explained in my presentation, the national institutes are by definition adjusting their clocks within a few nanoseconds. So even between the national labs, there are a few nanoseconds in their primary local clock ensemble. And with a accuracy spec of our RES 720 of 5 nanoseconds, that is pretty much the same. So yeah, we are within 5 nanoseconds accurate to GPS time, but the difference from there to another UTC clock is basically only known by the system operator. Yeah. So we don't know that. Yeah.
Awesome, awesome. Any more questions? Okay, great. Seeing none. Again, thank you very much for the presentation. Very informative. Really enjoyed it, and looking forward to seeing everyone in 2 weeks. Great.
See you. Thank you very much.
Bye bye.
Bye bye.